The topic of this first lecture is categories and functors, and as with many other mathematical topics, the first question is why should one learn about categories and why should one care about the definition of a category? The purpose of categories is roughly twofold. So one important motivation for introducing categories is that they serve as an organizing device for mathematical structures. So they allow to give very convenient and concise descriptions of complicated mathematical structures, and using the language of categories, many mathematical definitions become simpler. Another reason for introducing categories is that they allow to see similarities between different mathematical situations. They allow, for example, to carry over proofs from one mathematical setup to another, and this is why we care about them. So I'll start with the definition of a category and then soon continue with examples for categories. So here's the definition. Category C consists of the following data. It consists of a collection of objects, which is denoted by C bar. So it's an important point that I don't require this to be a set of objects. So collection here stands for what people sometimes refer to as a class, so a collection of mathematical objects that does not necessarily need to satisfy the axioms of a set. In particular, we will be allowed to consider the collection of all sets. So this is the first piece of data of a category. The next piece of data of a category is the following. It's a set Hom C A, B, and that's called the set of morphisms from A to B. And we have such a set of morphisms as our data for every pair of objects A, B in our category C. And the next piece of data we require is a composition law. So composition law, and this is now a function of sets. So it's a map that's denoted by circle. It goes from the set of homomorphisms in C from B to C times the set of homomorphisms in C from A to B, and it lands in the set of homomorphisms in C from A to C. And we have such a composition law for every triple of objects in our category. So for every triple of objects A, B, and C in our category C. So the last piece of data that we require a category to have are certain preferred morphisms, the so-called identity morphisms. So we require that there is an identity morphism denoted by it A. That's an element of the set of homomorphisms in C from A to A for every object A in our category C. So these identity morphisms only live in this morphism sets where the two entries coincide. So in general, we do not require that this set here has to be non-empty. We only require there to be a specific element in the case where A equals B. So this is the data of the category, and like it is the case with many mathematical definitions, we now require that this data satisfies certain conditions, and this is what I specify next. So this data has to satisfy the following two requirements. The first is that the identity morphisms behave like identity morphisms, meaning that for every morphism, F in the set of homomorphisms from A to B, we have that if we compose the identity on B with F in this way, then it's the same as F. And if we take first the identity on A and then compose it with F, we also get out F. And one should, of course, note here that for this formula to make sense, we have ensured that the identity of B and the identity of A have the property that these objects here coincide when you set in this formula here. So this is one requirement, and the last requirement in the definition of a category is the associativity of the composition, meaning the following, that if we are given three composable morphisms, so if we have an F from A to B, a G, a morphism from B to C, and morphism H from C to D, then it is true that if we first take the composite of F and G, that's the expression in this bracket, and then take the composite with H, then it's the same as taking first F and then the composite with H and G. And when I take the order of composition here from the right to the left, I follow the usual convention that the function that is applied first is on the right. And again, the fact that this B coincides with this B and the fact that this C coincides with this C ensures that this composition law is defined. So in general, we are not able to compose two morphisms if we don't have this object coinciding with this, but in these cases here, this doesn't provide any problems for us. Before I now come to the examples, I will present a little bit more of notation that I may have already used in words. There are many textbooks on category and many sources, and not all authors are completely consistent about the terminology. So for example, so here are some alternative notations. For example, it is common to say map or also arrow for what I now called morphisms. So this is a very common language. Another notation that one often encounters and that I will probably mostly use in the sequel is to simply write C, A, comma B for the set of homomorphisms in C from A to B. This is a shorter notation that's often convenient. It's also a notation that is also used in many textbooks is to write op C for what I denoted as C bar, which has the advantage that it doesn't collide with other uses of this bar notation. And another convention that many people apply is to omit the circle when it comes to the composition of morphisms and simply write GF for what I now formally introduced as G circle F. This, of course, implies that a specific composition law is understood that should have been made clear before. Okay, now comes a last formal definition that I would like to present before I start with the examples, for the simple reason that we can then recognize what I'm defining here in the examples. The definition is the following. We say that a morphism F from A to B in a category C is an isomorphism if the following holds. That is, if there exists a morphism G from B to A in the other direction with the property that both composites equal the respective identities, so meaning that GF is the identity on A, so that's a morphism that starts in A, goes to B. So the composite is a morphism that starts in A, goes to B, and then goes back to A, so this may or may not be the identity on A, and this is what we require when it is an isomorphism. And the other way around, we require that the composite, first G, then F, is the identity on B. So this is the notion of an isomorphism. By definition, every identity map is an isomorphism, but apart from that, a morphism in a category may or may not be an isomorphism, and there may be many of those, or just identity maps. So, and continuing this definition, we say that two objects A and B are isomorphic if there exists an isomorphism F from A to B. So, and this F from A to B, or G from B to A notation that I already used here, that's of course just another notation for elements in here. So what I'm doing here is I'm writing F from A to B, or also sometimes A goes to B with the arrow decorated by F if F is a morphism from A to B. So this is another notation I'm using. So two objects are isomorphic if there exists an isomorphism between them, and if we just phrase it this way, we don't specify the isomorphism. So in many situations, this is something one has to take care of whether there's a specified isomorphism or just any. Okay, this is now finally the point where I can start with the examples. One very obvious example that's in some sense the most basic one is the so-called category of sets. So this is a category denoted maybe by set, so the category of sets. This is the category whose objects are the sets. And this is the point where it becomes important that we did not require the collection of objects of a category to be set themselves, simply because there are contradictions that arise if you want to consider the set of all sets, but there's a broader notion of we call collection of class that allows to consider all sets. So these are the objects. The morphisms in this category, well, they are the maps of sets some people call this set theoretic functions. And here it's also maybe important to once note that we did require the morphisms between two objects to be a set, so we don't want to allow possibly larger notions of collections for these morphisms. There we require them to be sets, and this is of course clearly satisfied in this example. So the morphisms are the maps of sets, and the composition, well, that's the usual composition of maps. Well, the identity maps I don't specify explicitly because they are just the identity maps between sets that send each element to itself, but it may be worth noting what the isomorphisms are in the category of sets. So the isomorphisms in the category of sets, well, these are just the bijective maps, because a map of sets is bijective if and only if it has an inverse in this sense here. Okay, this is our first example. Now we will come to examples that have somewhat more structure than just sets. So the next example is the category of groups. So this I will, for the purpose of this lecture, denote by GRP. So this is the category of groups. As the name suggests, the objects in this category are groups, so sets equipped with a preferred unit element and a composition law that's associative, that makes the unit element into a unit element with respect to the composition law, and where you have inverses. So the objects are groups. The morphisms are group homomorphisms. So maps between the underlying sets of the groups that respect the composition law and the unit element. The composition is again the composition of maps, and this makes use of the basic fact that if you compose two group homomorphisms, you get a group homomorphism again. And of course we also implicitly use that the identity map is a group homomorphisms for very obvious reasons. So this fits into this general definition of a category, and the isomorphisms in this category group are just the group isomorphisms. So group homomorphisms that have an inverse or equivalent, group isomorphisms that are bijections on the underlying sets of the groups. So this is an interesting category. Another useful category is the category of K vector spaces. When K is a field, then we get the category that I will denote by vect K, the category of K vector spaces. So this is a subject of this category that implicitly known from linear algebra. So the morphisms, the objects in this category are, as the name suggests, the K vector spaces And the morphisms are the linear maps that are sometimes called vector space homomorphisms. And of course, we again implicitly use that the composition of two vector space is homomorphisms is a vector space homomorphism again, so that we can take the composition of these maps as a composition law for this category. Again, the identity is a linear map, that's also clear. And so we get a category, and we note that the isomorphisms in this category of k-vector spaces are the linear isomorphisms. So isomorphisms between vector spaces, namely those linear maps that have inverses. So that's a few examples that will be known from various earlier courses in mathematics, but in some sense these examples are slightly misleading because they give the impression that every category is of the sort objects are sets, possibly with an additional structure, and morphisms are maps of sets that respect this additional structure. And this is not at all true.
Can I ask a question?
Yes.
So if you have a category in an object, you can also consider isomorphisms to itself, right? Isomorphisms from an object A to A, and I think that gives you a group. Is that true?
Yes, this is of course correct. If you if you just consider the composition law in a category let's do it like this. If you consider the composition law just for one single object, then it becomes a function of this type. In general, this might not be defining group structure on here simply because we may not have inverses, but as you said, one can observe that the composite of two isomorphisms is an isomorphism again, and so this means that this composition law restricts to the subsets of isomorphisms, and this restriction, this now is a group law, and this way we can always distill a group from an object in the category. Of course, it may happen that the identity map is the only self-isomorphism that an object has. This is sometimes the case, and then this is not a very interesting group, but for example, in the case of vector spaces, this general observation here gives rise to the general linear group if we apply it, for example, to the standard vector space Kn.
Yeah. And maybe also a remark, if you just look at the maps from A to A with the composition, that is called a monoid, right?
Yeah, I'll come to monoids.
Sorry for that.
I'll come to monoids later, but
okay.
Yes, so
okay.
Set
Sorry
with such a composition now that doesn't have necessarily inverses, that's a monoid. Okay. But now we'll continue with groups and provide a different type of example for a category that's somehow, well, way smaller than the examples we encountered so far. So if G is a group, then we can build a category from this group as follows. We get a category that I denote by script G to distinguish it from the group with one object that I will just denote by star, And now when there's a category with just one object, there's very little data to specify for this category. So the only additional data we now have to specify are the homomorphism sets. But if there's just one object, there's only one homomorphism set. And this homomorphism set is the set of morphisms from the point to the point. And we set this set to be our group G. And now we have to define a composition law. So the composition law of homomorphisms in this category script G. So that's now a map of this type. And this we just set to be the composition law in our group G. And then we finally have to specify an identity element, but the group by definition comes with a unit element. And so the unit of our group G gives the identity element of our single object. And with this definition, we make sure that the identity has the required properties. And of course, also this example here generalizes in the sense that we could start with a monoid rather than with a group, because for this whole construction, the existence of inverses in the group is not relevant. And so this is the first example of a category that is not just sets with additional structure and structure preserving maps between them. I'll now give another, so to say, small example of a category. So suppose that P and lower equal is partially ordered set, then we can distill a category from this mathematical structure. So this is a category, gives rise to a category script P with the following properties. The set of objects of this category P, this is defined to be the set P itself. And now I have to specify the morphism sets in this category. And I simply do this by the requirement that the cardinality of the morphism set in script P of morphisms from A to B is defined to be 1 if A is less or equal B in this relation here, and it's defined to be 0 if this is not the case. So this means that this is a category with either 1 or 0 morphisms between two objects. And so the only thing we now have to check is that there are identity morphisms. So there's always a morphism from A to A. Well, this is true because partially ordered set comes with an equivalence relation that is reflexive. So it's always true that A is less or equal to A. So then there always exists a morphism. And we have now to make sure that we can define the composition. So and there it's a transitivity of the equivalence relation that implies that the composition is well defined. So if A is less or equal to B and B is less or equal to C, then we also have that A is less or equal to C, and then the two morphisms composed to the unique morphisms between the two.